Introduce myself. My name is José María Vega de Segan. I'm a researcher and head of the photovoltaic model group in Tecnalia. I'm the coordinator of BIPVBOOST project. This webinar is a consequence of this BIPVBOOST project. We are getting to the end of the project in May, and we have a series of webinars scheduled. This is the first one on digitalization, innovations and results provided by the project. And we will be having a second one on standardization activities on the 9th of May, and the last one on overall innovations on manufacturing and also BIPV system level and the cost competitiveness in Europe. So this will be scheduled probably during the 15th and 19th of May. We still have to decide the exact date, but this will be public webinars, upcoming public webinars for the project. So focusing on today's webinar on digitalization, I will provide an opening and introduction to the project. Then we will have 4 speakers, partners of the project, Philip Alami from Enerbim, who will present the progress on their BIM-based software tool. We will have Ricardo Alonso commenting on the activities of the project on the development of a BIPV digital twin and failure detection diagnosis tool. We will have also Mojtaba Eliassi from 3E speaking about a cloud-based energy management system for tertiary buildings, including BIPV generation, storage, and manageable loads. And last but not least, Erika Sareta from Subsea, who will present the development of the augmented reality in conceptual BIPV design stages. So we will leave questions and comments to the end. So I will proceed to the introduction presentation. I will share my screen. Let me make this full screen. Okay, so yeah, since I already presented the project, we are getting to the end of the project, and this is the first webinar on digitalization, innovations and results. For those who don't know the project, it is a H2020 project, which started in October 2098, and we are ending now in May 2023. The topic was demonstrate significant cost reduction for building integrated photovoltaic solutions. The project is coordinated by Tecnalia, and it's a consortium project with 19 partners covering mostly the most representative stakeholders and key players in the BIPV value chain in 7 countries. The title of the project is Bringing Down Costs of Multifunctional Building Integrated Photovoltaic Solutions and Processes Along the Value Chain, Enabling Widespread Near-Zero Energy Building Implementation. So at a glance, what we aim is to move from iconic BIPV towards the mass adoption of the technology in all segments of the construction sector. So we have nothing against iconic BIPV, but we are aiming to produce impacts that will allow the adoption of the technology in all segments, not only in this niche segment, but to extend the possibility of integrating photovoltaics in the residential, in the commercial, and also in the industrial segments. The main objective is to reduce the extra cost associated to the PV part by 50%. So it is an objective that was set, if I may again use, by the set plan for PV, and this is the main ambition of the project. So we propose a holistic approach of different cost reduction strategies along the value chain, starting with advanced manufacturing, following with the development of optimal BIPV envelope solutions, the implementation of digitalization strategies along the value chain, and also covering standardization activities for BIPV. So I will now present the main project results. Well, the first one will, of course, be the flexible manufacturing line for BIPV. We developed a new flexible tower stringer for crystalline silicon technology, which provided an enhanced flexibility in design and high productivity and quality, and ultimately a module cost reduction. We have an automatic string layup, which can accurately and freely position strings onto the module glass. In this case, we can go up to XL formats, 3 by 2 meters. We have also the possibility of implementing inline quality control strategies at string and module level prior to the lamination step. And we can be working in two operation modes, standard and customized. So with the standard functioning mode, we can be we can work at a higher speed, let's say, but less flexible. And with the customized operation mode, we can be much more flexible at a slower speed, and we can have customized string length. We can play with different cell distances, even inside the same string. So we can deliver highly customized string modules, sorry, at a competitive cost. The second main project result would be the portfolio of low-cost and aesthetical BIPV solutions. In this case, we have 4 main contributions. The first one from mitigation on the development of advanced glass-glass BIPV solutions based on crystalline silicon, back contact, and amorphous silicon technologies. We have also the contribution from PITS, an Italian company, which has developed a multifunctional BIPV facade cladding system with integrated insulation. Then we have also the collaboration between Flisson and Schweitzer from Switzerland, both companies. And in this case, they have developed a CIGS on metal solution compatible with facades and roofs. And next, we will have the low-cost click-and-go substructure for easy and fast installation from Tulips. Next, we have data-driven strategies for cost reduction along the value chain. This is basically the topic of the webinar today. We will be presenting the contributions from Enerbeam, 3E, Tecnalia, and Subsea on this field. The first one from Enerbeam on the progress of their software tool, BIMsolar. The second one, as I presented already, on a cloud-based energy management system for tertiary buildings. And from Tecnalia side, the BIPV digital twin and failure detection and diagnosis tool. And Subsea will present the augmented reality tool, which was also implemented in BIMsolar from Enerbeam. Next, on standardization, this was one of the topics that we worked during the project between Subsea, Tecnalia, and CSTV. As a result, we proposed new combined photovoltaic and construction testing procedures, including also the development of specific equipment for these testing procedures. And we worked on 4 topics: energy efficiency, energy performance in non-conventional scenarios, mechanical performance, and fire reaction for BIPV. As a result of this work, we have produced new testing procedures in each of these topics, and we are in direct contact with ongoing standardization activities. So in this case, we are in touch with all these ongoing activities and are now in discussion, in some cases, proposing the implementation of these new testing procedures in some of these new standards. There's available material in the public repository of the website. I will have a slide on this next. Then on demonstration activities, all the products that we developed in the project were taken to a TRL 7 and demonstrated in a real building. In this case, we have a bifacial balustrade glass solution manufactured by Onyx Solar, demonstrated in the headquarters of ISFOC in Puerto Llano in Spain, and also the walkable floor integrating back contact technology, in this case, also manufactured by Onyx Solar. This is well, the result of the collaboration between Onyx and Tulips for the demonstration of a glass solution, which uses the new flexible manufacturing line from underground assembly in some of the modules you can see on the screen, and also the click-and-go solution from Tulips, a very fast and easy system that allows very efficient installation process and also maintenance, since we can easily replace these elements. This is another picture of this demo site. Next, we have the CIGS on metal implementation in a residential building in Belgium, in Mons. And at last, the demonstration of PIT's multifunctional solution in Morbagno in Italy. So just to let you know that we have public material available on the website. We are providing public material on different topics, very interesting topics, and high quality contents are available for you to check on cost competitiveness, cost reduction roadmap for the European BIPV sector, market and stakeholder analysis, contribution to NZEP, standardization, digitalization, and more. So please go and check. And last, I will finish with this upcoming event. So we have this first webinar. We will have a second one on standardization on the 9th of May. Then we will have also a demo visit with stakeholders in Optimal Demo Site in Mons, in Brussels. If you are interested to attend, please let us know. We can see if this is possible, although the attendees are limited due to the space limitations of the building in this case. And we will have a last webinar on innovations at manufacturing and BIPV system level and BIPV cost competitiveness in Europe, probably in the week of the 15-19 of May. This is still to be defined. So please join us. And one last comment from my side: we will have an upcoming, well, a following project that will be also coordinated by Tecnalia. This project is called Seamless PV. It started in January of 2023, and we will be also producing public material that will be available as we progress with this project. And that's all. We can start now with the presentations of the speakers.
Thank you, Jose Maria. So now we would like to welcome Philip Alamy. I don't know if you have, you can share your screen or your connection is not so good. If not, let me know and I can share it for you.
No, I think it should work.
Okay.
I'm sharing the main screen, PowerPoint. Can you just tell me if you can see it?
Yes,
okay?
everything is good.
Good. So good day, everybody. It's a pleasure to meet you in this webinar and to present our achievements related to BIM-based simulation solution, providing performance to solar systems integration for a rebuilding context, which was our topic for this project. I am Philippe Alamy, Associate Director and Product Owner of NRBIM, and the product presented here is BIMsolar. The main target of BIMsolar is to be a complete solution dealing with urban values, urban shapes, architectural shapes, and of course solar potential, solar energy, and also designing, digital designing and addressing architecture, engineering and construction. So the digital skills were in charge of boosting integration in the AEC workflows for this project. First, with a huge support to concept design. Second, to enrich technical design, so following the reference workflows for the AEC world, connecting manufacturing, organizing the installation, the preparation of installation, and also anticipating operation and maintenance. First, to address concept design, we developed in this project a brand new tool, BIMsolar panel editor, a full web solution to anticipate the BIPV performance at element level. So you will be able to discover it at the end of the project online for free. This full web solution enables to create materials, transparent glass, colored glass with cells, variety of cells, density of cells, and representative cost and CO2 equivalent weight, and then connected to the later stages of the process. So first, this is the first innovation. The cost savings are, of course, the time to pre-design, the time to choose solution and to compare solution, not to install, the time to share and discuss and decide about the choice of materials, and the main gain is to be able from scratch to provide at this stage, the very early stage of the project, a BIM ready object and BIM ready catalogs of objects dealing later on with simulation and integration into the BIM workflows. Cost assessment, first cost assessment and first carbon impact, so are delivered at this early stage of the process. You will be able to find at the end of the project BIPVBoost, so the final delivery will be the official e-catalog of the BIPVBoost solutions as materials and panels, BIPV glasses like bifacial balustrade roof, walkable roof, solar tiles, cladding, insulated cladding. So the catalog is ready and is enriched with these objects and full online. From panel editor to total BIM, the collaborative workflows is supported by our tool, desktop tool, BIMsolar, that was enriched during the project. The materials must integrate the building, so BIMsolar imports either non-BIM or BIM CAD models from architecture or urban forms to support BIPV concept design. So the process is in picture of the following. Of course, for this optimal house demo site number 3, we started from the existing roof. We designed with the architect the 3D model. In this case, it was with SketchUp, but also with the Revit BIM solution. Then we gathered elements, information, data to provide the first design of the material, the tiles, CIGS tiles, and then we replicated and simulated the roof with all the key performance indicators to assess the performance of the installation at concept design. So a lot of data, a lot of information gathered in this very early stage and critical stage of the process. Step by step, BIMsolar desktop enriches the design in 7 steps. First, the development of the material from the online panel that you've seen before, with lots of features and more accuracy in dimensions, electrical parameters. Then the simulation of solar potential to detect and display and calculate, of course, the shading effects, the losses and the gains. Layout design with the modules pre-designed and developed at the BIM object. So here you can see the cladding, insulated cladding from PIS on the more new buildings. The electrical production, connecting strings to MPPTs and inverters, and dealing with all possibilities of stringing and comparing strategies to avoid mismatching effect, for instance, and then the KPIs and a good possibility to optimize and to deal with the scenarios like self-consumption scenarios, because we will we will feature at the end of the project the first prototype of the optimizer engine from Optimal and the Edge HP heat pump consumption model from UREC. So all is connected in one software, connecting panels, materials with the architecture, the 3D model, and you get the results. And this is new, and this was the main achievement of this project, dealing at concept design with the maximum value and also replicating the BIPV enriched model to the BIM solutions. The cost savings are still important in time to pre-design, to optimize, and the gains are mainly BIM-ready layouts, because all that you can see here is replicated in the main BIM solutions, private BIM and open BIM. And the unique workspace saves times and gains in collaboration, of course, and delivery of multiple KPIs. The technical design is fine-tuned in the solution from, of course, traditional methods, dealing with a lot of variables, data, but enriched with BIM and 3D designing, 3D modeling, always dealing with high accuracy and a lot of parameters that you can see on the picture between the element level and the building itself, all in virtual, because BIPV needs multidisciplinary tools and studies as a multidisciplinary material, multifunctional material. Another achievement in this project was to build a unique CAD-to-CAM BIMsolar panel editor to manufacture the BIPV glass that was designed in the same time that the BIPV project was designed. So we can see on this picture that we are analyzing the traditional datasheet from the manufacturer, the producers of BIPV glass. For instance, this is the Demo 2 glass from Onyx Solar, red glass with a large choice of positions in cells, rows of cells, and then we built a tool able to read the data and translate the data into machine language to launch the fabrication line directly. So it's a kind of design to machine tool. And this was a great ambition. And now we have the first prototype. Of course, it's highly specialized. It's not a very public tool, but it's connected also to the BIM workspace. So cost saving are here again, time to pre-design, time to optimize, and the risk of avoiding issues with manufacturing. And of course, no delay to share a design with a manufacturer process. And the gains are adaptable XML format. I say here, this format enables the adaptation to every kind of situation of manufacturing, because it's a very easy to handle format. It's not very specific, so you can afford a dependable coding. And of course, you keep the BIM readiness from CAD to CAM. Installation with BIM is a question of organization. So this is more traditional, but we supported one demo site in this way, the Optimal demo site in Belgium. We made a full modeling with a BIM tool, Autodesk Revit, that proves that we are able to handle, of course, 3D modeling and dimensions and lots of data between panels, electricity, of course, wiring, electricity features, but also the management of a planning and the fourth dimension of BIM, which is time. So the BIM platform are becoming the new collaborative workspaces, and this is useful and very appreciated to support the preparation of installation of complex BIPV layouts, because you can attach to the BIM model notices and guidelines, and then you can gather all the information in one workspace, and it's a collaborative workspace. And you can use also 3D viewers, so non-sophisticated information online, but 3D viewer to organize the works on site. And you can report clash detection and report, of course, the contextual and the issues in real time from the works and to the back office. So a lot of cost saving in time, of course, in risk mitigation, and gains in feedback, traceability, planning, quality, knowledge, of course, and commissioning, because the models are saved, the projects are saved, and you can access the model online or as a desktop solution with all the enrichment of data, leading to the last achievement we made in this project, the connection of the BIM tools and BIMsolar in particular to digital twin addressing operation and maintenance for BIPV. So together with Tecnalia, presenting the tool in more in details after me, we are able now to translate a project, BIPV project, from design to construction to operation and maintenance through a kind of simplification, because there is no more the need of a complete 3D, but a more analytical model able to feed routines, analyzing failure modes, and detecting the effects of these failure modes. As you can see, we can analyze, and this is the job for Tecnalia. Analyze the IV curves module by module or string by string, and of course at installation level. So this is the connection of two workspaces: the real-time workspace and the project workspace with that data and dynamic data, of course. Success story in this project, of course, as are the demo sites, because we designed and co-designed and developed the virtual significance and simulations, connected simulation of each demo site. So you can see ISFOG, Mondragon, Optimal, and PIS, with modeling in 3D, of course, modeling of element level, innovation in developing families of complex objects like the tulips plus Onyx Solar glass family in Revit, like the Schweizer Flitstorm CLGIS tile and framing and mounting system, and also of course, the workable floor and the bifacial balustrade of ISFOG and the insulated cladding of PIS. So all the objects will be delivered in the e-catalogs as virtual objects. And last but not least, we also developed for the PIS building a virtual mixed reality effort and proof of concept, enabling the fact of making choices in front of a building with a large variety of modules and solutions applicable, overlapping on the facade, for instance, in this case. Success story in an open market to finish. The software is used by normal users, not only in the project, of course, but for big or normal project. The biggest project today is the Olympic Games swimming pool in Paris, with a complex 3D roof with BIPV panels, not BIPV panels, but complex BIPV panels, and sophisticated BIM, and also normal projects like schools and atriums, for instance, on the right of your picture. As a conclusion, I would say that BIM and the BIM tools are a new paradigm to boost the architecture, engineering, construction, and PV integration, because it can join the traditional processes with a lot of innovation in 3D and in data creation and data gathering, of course, and data exchanging. Autodesk runs the market with Revit, so it's difficult to avoid Revit, even if we need to go open BIM, of course, but this is not a barrier, I think. So we are developing technologies to be compatible with Revit and compatible with the open BIM, IFC in particular, of course. BIPV has to BIMify, we think, since the first concept design, because concept design is very critical, of course, with a lot of data, lots of choices to make, and BIM is a good support, a strong support to save time and to mitigate risk. Parametric objects are a good opportunity because of their multifunctional character, like the BIPV modules, for instance, are today. because adapting to the contextual situation of the design. And there is a fantastic potential of saving and gains because even if the interoperability between tools is still a challenge, the digital workspaces, the teams are progressing and the database are compatible now. So we can progress a lot and we can prove it in this project. So at the conclusion of the conclusion, BIMsolar is today the unique BIPV solution compatible with the tools and the formats, creating BIM for BIPV from scratch, because we can create the modules online from scratch and connected to the architectural works, of course, or the urbanistic values, with a continuous design to operation and maintenance process. And I thank you for your attention. And I'm Philippe Alamy, and I am from NRBIM. You can join us, of course, through the website of the BIPVBoost project.
Thank you, Philippe. Now we give the floor to Ricardo Alonso.
Thank you, Yasmin. Let me share my screen. Okay, here we are. In full screen?
Yes, we can.
Perfect. Good afternoon, everyone. First of all, let me introduce myself. My name is Ricardo Alonso. I'm in charge of the research lines in Tecnalia of energy conversion and operation and maintenance of photovoltaics. And I'm leading in BIPVBoost project. I'm leading the work package focused on the digitalization for the operation stage. So in the previous presentation, Philippe has presented what the digitalization can provide during the design, manufacturing, and installation stages. And now we are going to see what happens after the commissioning of the PV plant. Which is what can the digitalization also help us during this stage, during the operation of the system to enhance, to improve the profitability of this kind of systems? So obviously the answer is yes. We have to take into account that at this stage there is a new data source that is huge, that is the monitoring of the real performance of the system. And if we apply the suitable data analytics techniques to this, we can improve the BIPV model developed in NRBIM to represent more precisely the real performance of the system. So this way we can detect potential anomalies and their performance in the system and to trigger some alerts warning about failure appearance. Of course, this will lead to a better operation and maintenance, because we will reduce the cost of this operation and maintenance, as in this kind of systems, the inspection techniques on field are quite expensive. And on the other hand, we will improve the performance ratio, because otherwise there are some failures that will be unnoticed. Apart from this, if we feed also this enhanced BIPV model, representing more precisely the real performance of the system with weather forecast, we could offer a more precise BIPV forecast also. That is essential in order to implement a predictive building energy management system that will try to get the most from the BIPV production for the profitability of the system. This will the scope of the next presentation in any case. But I'm going to focus in my presentation in the failure detection and diagnosis functionality, because from my point of view is the most valuable added value of the BIPV system, because for the BIPV forecast there are other solutions in the market that presents similar results
because at the end, the main uncertainty of the forecast is determined by the weather forecast. So at the end, to have a better BIPV model is not so important for this. So let's focus on the failure detection and diagnosis functionality. The first question is, what is a BIPV twin? Well, it's not only a physical model. So a physical model is the BIPV model that Philippe has presented us. So it's a simulation that describes the expected performance, the ideal performance of the asset. And of course, this can be used and is used in some commercial solutions for failure detection, comparing the output of the model with the monitoring information. And this will give us the opportunity to detect anomalies, but will not provide diagnosis. There is another approach, that is the data-driven models. Neither the BIPV data twin, neither is it a data-driven model purely, because in this case, the model is a black box where the different correlation between the input and output variables is determined. And this way, we will model very precisely the real performance of the asset, and we will be able to identify any anomaly, but we will require large data sets to characterize the normality. And also, in order to get the diagnosis, we will need a failure labeling carried out by experts previously. So, which is a BIPV digital twin then? It's a combination of these two previous models, a physical and data-driven model, in the way that we calibrate the physical model with the monitoring data we obtain from the field. So this way, we model the real performance of the asset. We are able to identify anomalies. We can include the diagnosis, the automatic diagnosis on this, because the physical model is self-explanatory, and we don't need these required large data sets that data-driven models need. But probably the main disadvantage is that this can lead to potential errors in case of unexpected anomalies appear that are not presented in this physical model. Well, we will see that in our case, we are covering most of the failure modes, but it's true that, for instance, the problems related to the data acquisition equipment, for instance, will lead to a bad performance of the BIPV data twin if we don't take this into account. So one of the questions we are going to see is that we have to ensure the data quality of the input data we are introducing in the model. So how we have transformed the BIMsolar physical model we have seen before into a BIPV digital twin. Well, this is the general scheme. It seems quite complex, but at the end are 5 functional blocks mainly. The first one is the data preconditioning. So we need to ensure, as I said, the quality of the input data we are to introduce to the model. So normally we have the PV system configuration, that this is the data in the contextual data introduced by the user, but then the monitoring information of the predicting condition, this is the weather data, and the SCADA production at the end, the voltage and currents provided by the inverter. So then we have to run the BIPV model with this weather data as an input in order to get the results and to compare with the data of the production of the BIPV system in the reality. If we see that are quite similar, we can say that our system is performing very well, ideally, and there is no failure detected. But in most of the cases, we will see that there is some difference between the output of our model and the real data. So we have to recalibrate the BIPV model in order to get a better representation of the reality. And for this, we have 2 stages. First one, a first estimation of the parameters of this model, and then an iterative process with an automatic optimization loop where these parameters are refining. Once we have the system calibrated, the model, this will give us information about the real performance and also about the state of the health of the different elements, and this will be seen in the parameters that we have calibrated. So we will run some algorithms in order to detect potential failures and also to identify the root causes of these failures. So this is more or less the general idea of the BIPV digital twin, and now we are going to see step by step each of these functional blocks. As I said, one of the main questions is the problem with the input data quality. So we have to develop automatic tools for this. Here we have an example where we have some misalignment between the calibrated cell measuring the irradiance and the current of the PV array. So this will lead to this kind of dispersion in our models where we are trying to analyze the correlation between the irradiance and the current. And of course, here there is no way to extract the right conclusions. So we have to correct this, to detect firstly, and then to correct. And well, we have developed this tool for this. And apart from this, apart from improving the quality of the data, we can trigger an alarm warning to the demo site owner that we have this problem. In fact, this is one of the little failures we have detected, and this was checked and confirmed by the demo owner that there was this misalignment between the calibrated cell and the plane of the array on the roof. Then when we have checked this input data quality, we have to have a first estimation of the parameters of the model. So how we do that? Well, we have to extract from the voltage and currents the information to calibrate the parameters. And for this, we have to work because here we have the current in the above, and in the bottom we have the voltage of the roof of one of the demo sites of the project. And as you can see, well, probably you can see anything here, but not only due to the size of the picture, but also because there is partial clouds in some days. In other days, hardly irradiance. Other days are more sunny, and well, we can see hardly anything here. But if we filter the clear sky conditions with the suitable tools, we can analyze separately the voltage and currents. And we, for instance, if we analyze the voltage, we can even with the suitable clustering method to distinguish between the open circuit voltage that will give us a lot of information about some particular failure modes. And this will give us the parameter for the open circuit voltage in the single diode model of the PV modules, and on the other hand, the maximum power point voltages. And the same for the current. As you can see here, we have, with all the filters, we have obtained very good correlation between the irradiance and the maximum power point current. So once we have this first approach of the parameters of the BIPV model, then we run automatic optimization techniques to reduce the distance between the real monitoring data and the output of our BIPV model. For this, we have to define some metrics in order to analyze this distance, this divergence between both data sets. And the relevant aspect here is that we include also the heterogeneous conditions that will give us information about potential heterogeneous degradation in the system. So we are working at PV strength level or PV array level from the voltages and currents measured by the PV inverter. But for instance, in this roof that is west oriented, we have in some moments that in the morning that this partial of the roof is shadowed. So this means the BIPV model will give us information about which PV modules are shadowed and which are sun. And from the voltage measured at this instance, we can distinguish between the contribution to the voltage of the different modules. So we can add, in spite of having only information at the string level, we are able to distinguish effects at module level. Finally, how we detect the failure modes? Well, at the end, we analyze the potential deviation of these parameters that we are calibrating. So once we have the BIPV model calibrated and fitting with the real monitoring data we are measuring in the field, we try to analyze this potential deviation between the test parameters and the design specifications on the one hand, on the second one, between adjusted parameters of similar PV modules, and also how these parameters evolves along the time. So, and if we see significant deviations, we will trigger an alarm. Apart from this, once we have this detection, as the different failure modes will have different footprints on these parameters. So this means that they impact differently to the different parameters we are calibrating. We can distinguish between the different failure modes and the root causes. So in order to recommend some operational maintenance actions to the demo owner. So to conclude, what we have learned so far. First of all, that the BIPV that doing shows a great potential for early failure detection and diagnosis. This is evident. We have detected that there is a high impact of the data quality and also operation conditions. That means that if we have always shadow conditions or always cloudy conditions, it's more difficult to get right conclusions from these data sets. But in order to avoid these issues, we have developed automatic tools for this input data filtering and quality assessment that are working quite well. Then the fine-tuning of parameters after this first estimation we did is not a straightforward question, and it can be improved by means of new metrics and procedures that we are working on. And also the failure detection, the failure diagnosis can be also improved because although I said the different failures have different impact on the parameters, it's true that there are several failure modes that can have similar footprints in these parameters, but it's also true that this footprint is different along the time. So they have different time evolution. For instance, is different a problem of yellowing of the PV module than soiling that will disappear with a rainfall event or a cleaning process. The same happens with the shadowing. It's not the same partial shadowing that a source circuit bypass agent. Probably the effect is the same in the data, but the evolution of this effect along the time is different. So we have to work on specific algorithms for identifying these particular failure modes. And finally, well, it's also needed new procedures for the extraction, transforming, and loading of the monitoring data in the tool, because now it's a semi-manual process that is quite time-consuming, and also in order to show the results, the conclusion from this BIPV data to the end user, we have to improve also this to enhance the user experience. And that's all from my side. If you have any question at the end of the session, I will be at your disposal to answer. Thank you for your attention.
Thank you, Ricardo, for your presentation. Now we go to the next presentation. Welcome.
Do you see my screen?
No, yet we just can see you. Now we are, yes, now we can. Thank you, Modiava.
Okay. Hello, everyone. I hope you're all having a great day. I'm very excited to be here to discuss about or new services and products that we have worked on and we have been working on in the context of BIPV Boost project. My name is Moshtaber Yassi. I'm Asset Flexibility Product Owner at 3E. I would like to give you a brief introduction of our company 3E, founded in 1999. We started our digital journey in 2010, launched our first digital twin performance model of PV systems in 2012, and then we extended and actually we improved our digital twin by adding new services like solar data services and solar analytics. And in 2020, we surpassed actually 10 gigawatt of connected assets to Synaptic. And in 2021, we launched our new platform. In 2022, we improved it by adding new assets like wind and storage. And where we are actually with a headquarter based in Brussels, we have several offices as you could see in this world map. And we are also active in over 100 countries with more than 90 gigawatt renewable project and with 5 spin-off. What I would like to bring into your attention here is Delta Q, which is one of our spin-offs, and you will see later why. So basically, we have two categories of services: digital solutions, which is actually our Synaptic platform, go to digital, via which we can actually maximize your asset value and we can digitalize your renewable asset, and our expert services divided into, let's say, consultancy services for engineering, for technical advisory, and also for political and strategic advices. So herein you would have a better look over different services that we can propose, we can offer to our customers, from concept and design to operation and end of life. A bit of statistics for our expert services and then for Synaptic. And what I want to bring into your attention in this slide is our 5-minute typical data frequency and 15 minutes time series. And you will see why in the next slides. Okay. Thanks to BIPV Boost, we had to make a paradigm shift in the Synaptic platform actually, because as you have already seen in the previous slide, for BIPV Boost, we had to shift from offline data to real-time data monitoring, and we had to move from static policies to dynamic policies, and then we had to move from no operation to a dynamic operation. And in the right side, you could see how our asset flexibility product is envisioned. So we decided to take a methodological approach to analyze and specify different functions, technologies, and applications that we need for BIPV Boost project. I have listed different products that we have worked on: battery performance monitoring, real-time scheduled monitoring and control, load and PV forecast engines, flexibility optimization engine, and finally simulation. So thanks to this new product, we achieved some new KPIs as well. We want to compare what we have today and what we had previously. So we achieved granularity of 5 seconds and also update rate of 5 seconds, which was 1 minute and 5 minutes before respectively. And then the response time to control signal is mostly less than 30 seconds. There are some spontaneous responses as well, considering different power plant controllers that we have on site. And also network utilization, as you see here, we are approaching almost 1 megabit per second. And we also increase our availability by new edge device, and at the end, we significantly reduce the configuration person hours for any new plants. And we also needed a better security posture. And thanks to CloudGate, we deployed a new client server certificate-based security enhancement. Synaptic API is sending the certificates, server certificate, to the BIPV API, which is communicating with the CloudGate device. And after confirmation and validation, the client app actually sent its client certificate. And thanks to CloudGate and integrated with BIPV API at the edge, level, we have a stable, a scalable, a remote, and a reliable solution. The next step about improving our consumption forecast. Actually, we started with similar day approach as a benchmark, and then we continued our exploration by trying different approach, SVR, support vector regression, ARIMA, and SARIMAX, some regression-based approach. And at the end, we came up with a hybrid approach by which we make a simple forecast using SARIMAX, and then we improve our forecast using a machine learning methodology called BIPVBOOST by predicting the forecasting errors. So here you can see some results, the way that we could improve our consumption forecast by using a hybrid method. And then on the right side, you could see the productized forecast of Synaptic. Also, PV production forecast, in line with what Ricardo mentioned for the digital twin. Actually, we have we had a very well-developed digital twin for PV. We have been working for years on that, but then we decided to move from white box model that we are using currently to a gray box model. So again, using gradient boosted trees or BIPVBoost, we tried this new methodology over different sites in Synaptic, and here you could see some exemplary result and the way that we improved our forecast here. And you could see here the collaborative scheme and the sequence diagram between Delta Q and Synaptic in order to achieve this cooperation. And finally, to give you a visual presentation of the result, you could see here in 3 different use cases: baseline separated energy management systems and combined energy management systems, how the comfort could be preserved and the battery could be rescheduled to get coordinated with the HVAC consumption result. In that case, we are stacking different, let's say, value propositions from thermal inertia of the building, from battery management system, by leveraging local PV production and using time of use tariffs. That's it from my side, and thank you so much for your attention.
Thank you. Thank you so much for your presentation. Now we give the floor to Erika Zareta. Welcome.
Okay, can you see my screen properly?
Yes, we can.
Okay, so good morning, everyone, and thanks to be here. My name is Erika Zareta, and I am a researcher at SUPSI, Southern Switzerland. Today, I'm going to talk about an application of the augmented reality technology on a real BIPV building of the BIPVBoost project. So talking about augmented reality, mixed reality, and virtual reality can be a little bit confusing. So I would like to make a brief overview of these technologies. So let's say that extended reality refers to all these real and virtual environments, a kind of, let's say, umbrella category that covers all the various forms of computer altered reality. So we have virtual reality, we have augmented reality, and finally mixed reality. So briefly, virtual reality is a technology that gives you the sensation that you are completely immersed within a virtual synthetic 3D environment that is entirely generated by a computer. You can experience it with headset and hand controls, and you are really within a virtual world. Then we have augmented reality that superimposes digital information generated by digital tools on the top of real world. And this is specifically developed to be visualized on smartphones and tablet screens to project the image in a limited area in front of your eyes. And augmented reality can be, let's say, a kind of superimposition of a small digital object on a real environment. And finally, we have mixed reality, where the digital objects are placed in a real environment, so they can appear to be really objects, and the user can interact with them as well. So you have holographic headsets like smart glasses, and you can have a see-through display with digital contents projected into the real world. And it can blur the difference between what is real and what is not. And saying that, this technology can change radically the architectural and construction sector, since different stakeholders can get immersed in a virtual project during the various stages of the bidding process. So we have different application, but also different benefits that can regard the visualization, communication, but also training and project management, construction management, site safety, and so on. So what about photovoltaics and building integrated photovoltaics? So far, these technologies have been applied to PV for planning projects, for training, for maintenance. But what about specifically BIPV? So if we consider the whole BIPV process, you know that there are different process stages, starting from the strategic BIPV planning. Then we have the conceptual BIPV project, technical BIPV projects. Then we have finally the installation, the O&M, also through digital twins. And then we have the end of the life of our project, that is dismantling and recycling. And in this project, we focused mainly on the conceptual BIPV project stage, because typically this is a stage where we have iterative design, where a lot of efforts are spent by architects and consultants to investigate different BIPV solutions, for sure, but also to communicate efficiently the BIPV projects and its characteristics to clients. And we have to consider that usually clients are not used to 3D drawings and 3D representation of projects. Architects, the majority of them, let's say, are used to provide drawings, renderings, preliminary data from initial simulation as to the objects, so as to the media. And it arises that mixed reality, for instance, can effectively communicate the 85% of information to the client versus the 70% provided by 2D media. And so it is important to involve client in, let's say, quite new topic of BIPV, to let them understand what BIPV is, and to try to overcome this stage with reduced effort in the communication of the project, so that we can have a go from the client to go for a BIPV project. So we investigated the most important data and information to be included in these new technologies. We try to involve not only partners within the consortium, but also external partners, so stakeholders outside our consortium, to get the most important aspects. And it arises that we have different priorities, and we noticed that highest priorities concern PV production, PV yield, so not very detailed information, but mainly we need to provide BIPV module geometry, BIPV module colors, customizable options. So we need to focus our attention on aesthetical appearance. Later on, there are for sure also other aspects that involves the solar radiation, the building geometry, the sun path, shadings, and so on, but also the costs, the extra costs, value about payback time, life cycle data, and so on. But we have at least this overview of what concerns the most the BIPV stakeholders. And for this reason, we started to develop a first proof of concept for mixed reality for BIPV. And the goal was to understand the potentialities of such a technology on a real demo building of the BIPV Boost project. So we developed this proof of concept and we organized 4 main stages for the development. So the first one is the BIM modeling of the existing building in Morvegno, Italy. And we use this BIM model into BIMsolar to provide some BIPV design scenarios. We developed different BIPV solutions. We simulated it, and we include also the final solution that has been applied on the real building as a result of the project. And then, thanks to the interoperability with Revit, these BIPV design scenarios were imported in the BIM software, and specific BIM and geometrical formats were exported in order to be, let's say, compatible with a cloud platform provided by a technology provider, AFCA, that allows us to visualize this digital model developed between SUBSEA and NRBIM into a mixed reality tool. And indeed, at the end, we create these models and we include them into this AFCA web platform. That includes also georeferencing features. So this is the workflow, and I'm going to show you the result of this, the implementation of this workflow. I try to. So as you can see, this is a view from the user who is using mixed reality. You can see that the building model made in BIM is overlapped to the existing real building, thanks to the georeferenciation. Then with hand controls, you can visualize only the digital model about BIPV. You can see on the top of the building BIPV modules that have been developed within the BIPV Boost project. And the peculiarity of this technology is that you can move and walk around the building, and the BIPV solution remains, let's say, attached to the building. The virtual BIPV solution is attached to the building. You can see these modules that are made of green, gold cells with white background, but you can also change the design solution. You saw that we change the appearance of the proposed solution. And different stakeholders can visualize the same model in real time, so you can discuss with the client inside the different BIPV solutions and also the most feasible ones. Then with the client, the architects consultant can showcase also the characteristics of the project, the BIPV module characteristics, and so on. So you have different options to better communicate what you have developed. And finally, you can also integrate data and color maps representing the simulation, or also in the next stage, we could also integrate shading models and shading information. So let's say that in this way, also people who are not used to 3D representation that is very common in clients can really be aware of the final result of a project. And this can definitely improve the communication and reduce also the misunderstandings with clients, building owners, so that we can really go for BIPV and support BIPV implementation. So with this proof of concept, we noticed that there is large potential for BIPV, and for sure there will be further developments such as the improvements of the background workflow with NRBeam, but also the idea of extending this experience also to other devices. But we are quite sure that this technology could support the improvement of the iterative conceptual design stage, supporting a positive decision by the client or building owner. So I would like to thank NRBeam who collaborate with us, and also AFCA who provided the technology for this mixed reality. And thank you also for your attention. I will remain here to answer any question.
Thank you, Erika. Thank you, Erika. Now, if anyone has any question or any comment, feel free to talk or write it in the box, questions and answers. No one has any comment?
I can step up and
yes,
ask a general question. So in BIPVBoost, we have reached a state of development which is probably a first step in some cases, an evolution and first step in some cases. In other ones, we might be closer to a final product. Which are the next steps you foresee for these developments? If you can briefly comment on that, each of you, 1 minute maximum. We can start with Philip.
Yes, in 1 minute. Well, the future of BIM is to add more dimensions, and then to add, for instance, of course, cost management, LCA, so life cycle analysis of the technology, the products, the materials. So translating, switching BIM to product life management, because this is very important for the building wall life management, to be able, since the concept design, to handle all the variables and the strong parameters to anticipate the performance, not only economical performance and electrical performance, but also carbon weight and all the sustainability of and durability of the design.
Thanks, Yep. Ricardo?
Okay, in my case, I think I give some tips on my last slide of the presentation. Main improvements that we need to implement is probably regarding the diagnosis, especially when there is simultaneous failure mode appearing in the system. And also regarding the integration, well, we have developed this in cooperation with NRBIM, of course, to introduce, but we have to improve, as I said, also the procedures for the automatic extraction, transforming and load of the monitoring data in the platform, and also to show better the results, the conclusions from these failure detection and diagnosis algorithms, I think.
Thanks.
Yes, I can continue. Actually, at company level, we need to improve our battery asset operations first. And then we need to have a better, let's say, digital twin of our battery energy storage system. And the next step would be analyzing how to give that flexibility to the grid instead of only using it on the local level, local system, but also we can somehow support the grid if there are ways to do so. And we would also like to extend our optimization model and also our forecast engines by considering other use cases, other similar use cases, rather than only a tertiary building, but also going into, let's say, utility scale plants and storage as well.
Yeah, so regarding mixed reality, there are different improvements that can be done. One of the most important is to extend the use of this tool also to other devices like tablet, but also to connect it directly to BIMsolar together with NRBIM in order to enlarge target audience, architects and consultants, so that they are better supported in involving people understanding and adopting BIPV.
Okay, thanks. I don't know if we have further questions. Otherwise, I think we can close here. I want to thank the speakers again, and also the European Commission for the support in the implementation of this project. So, as I said, stay tuned since we will have upcoming webinars. Yes, thanks, Jasmine. We will have one covering standardization, innovations and results covered in the project, scheduled on the 9th of May at 12 again. So I hope we can see each other again soon.
Yes, thank you so much also for the presenters. It was really great webinar, and remember that this will be available on social media and on the website of the project. So thank you and see you on the 9th of May.
Thanks, Jasmine.
Thank you very much.
Thank you.
Have a nice day.
Thank you.
Yes.